In this video, we are going to continue with looking at properties of power series. So let's look at theorem 6.3, multiplying two series together. So suppose that we have the power series, the sum from n equals 0 to infinity is c sub n x to the n, and the sum from n equals 0 to infinity of d sub n x to the n, and they converge to f and g respectively. F and g are functions on some common interval I. And we're going to define E sub n as C naught d to the n, d sub n, plus C1 d sub n minus 1 plus C sub 2 d sub n minus 2, and so on. So notice what's happening with those um, subscripts there. So I'm starting at C sub 0 or C naught, and then it's multiplied by d sub n. And then the C is going to increase by 1, but the D is going to decrease by 1 for the subscript for each of those terms. So if I'm multiplying these two power series together, C sub n x to the n and D sub n x to the n, then what's going to happen is I'm going to get a new power series with subscripts of terms that look like this, that E sub n to the n. And that is going to converge to the product of f and g on that common interval I. So I'm going to show you this in Wolfram Alpha. So I'm going to go to, so I expanded a few terms. So if I go back to my notes and I were to write out a few terms here. So let's start with n of 0. I would have c naught or c sub 0 x to the 0, which is 1, plus c1x plus c2x squared plus c3x cubed, and so on. That second series, if I were to start expanding, I would have d naught plus d sub 1x plus d sub 2x squared plus d sub 3x cubed, and so on. Question is, what happens when I multiply this expansion by this expansion? And you're going to see how those coefficients are going to look like this with that pattern. So I've got c naught plus c1x plus c2x squared plus c3x cubed, and then I've got d naught plus d1x plus d2x squared plus d3x cubed. And I just expanded the first 5 terms for each, and I used Wolfram to do the heavy lifting for me. And it did give it to me in reverse order, so I'm going to start down here. So this would be my x naught term. Okay, these two right here, let me see if I can write on this. These two, if I were to factor the x out, you can see how I've got C1 times D naught plus C naught times D1. So you can see how those subscripts are increasing and decreasing. Same thing here. It's following that pattern that they were talking about a minute ago. So we've got C sub 2 D naught, C sub 1 D1. So see how it increased for the D and decreased for the C. And then we decrease again for the C and increase for the D. If I were to factor that x squared out. Same thing with the x cubed terms here. So I started with C sub 3 D naught, and then C sub 2 D1, and then C1 D2. So the C's are decreasing in subscript, the D's are increasing in subscript. And that's going to happen for all of those expansions and that summations. You can see it here with that x to the fourth coefficient also. If I were to factor the x to the fourth out of those terms, it follows that same pattern. And that's really all that theorem is trying to say there. Is that pattern is going to exist here. So let's look at an example. We're going to multiply the power series representation for 1 over 1 minus x with the power series representation of 1 over 1 minus x squared to construct a power series for the function 1 over the quantity 1 minus x times 1 plus, times 1 minus x squared on the interval from -1 to 1. So I want to start by talking about where everything is coming from. This 1 over 1 minus x we're going to see a lot. if we're thinking about that geometric series, a times r to the n, that equals a over 1 minus r. In this case, my r is equal to x, and my a is equal to 1. So I can write that as the sum from n equals 0 to infinity of a, which is 1, times r to the n, which is x to the n, which is where they're getting that that rational function is equal to that summation. It's writing it in terms of that geometric series. And if we were to multiply that or write a few terms out, when we plug in 0, we would have x to the 0, which is 1. If I plug in 1, I would have x to the first. If I plug in 2, I get x squared. 3 gives me x cubed, and so on. And if I were to tweak this guy, let's replace this x with an x squared. And then I would do the same thing here. I would replace this x with x squared. So this is the sum from n equals 0 to infinity of x to the 2n. When we have a power to a power, we multiply those powers together. And then if I were to plug in 0, I would get x to the 0, which is 1. If I plug in 1, I would get x to the 2 times 1, which is 2. If I plug in 2, I get x to the 2 times 2, which is 4. And if I plug in 3, I would get x to the 2 times 3, which is 6. So that's where the series are coming from. We can tweak series. If I want something that looks like this, and I know this, I can just figure out what would I need to replace in what I know to figure out what my new series would be. Okay, we could also think about it as that geometric series and writing it that way again. So you've got a couple of ways to think about it. So we want to know, how can we use this to help us construct a power series for f of x equals 1 over 1 minus x times 1 minus x squared. Well, that's really 1 over 1 minus x times 1 over 1 minus x squared. And I have a power series representation for each of those. So this is a sum from n equals 0 to infinity of x to the n times the sum from n equals 0 to infinity of x to the 2n. So let's do an expansion here. Let's multiply a few terms out. So when I look at x to the n, we came up with a few terms. 1 plus x squared plus x cubed, and so on. Then we're going to multiply that by the expansion of x to the 2n, which was 1 plus x squared plus x to the 4th plus x to the 6th, and so on. And we're going to use our distributive property. So I'm going to start by multiplying everything by 1. So 1 times 1 is 1. 1 times x squared is x squared. And then 1 times x to the 4th is x to the 4th. And 1 times x to the 6th is x to the 6th. I'm going to move on to x. X times 1 is x, and I like to line things up vertically. X times x squared is x cubed. X times x to the 4th is x to the 5th. And x times x to the 6th is x to the 7th. And then x squared, distribute to that second parentheses. X squared times 1 is x squared. X squared times x squared is x to the 4th. X squared times x to the 4th is x to the 6th. X squared times x to the 6th is x to the 8th. And then distribute the x cubed. X cubed times 1 is x cubed. X cubed times x squared is x to the 5th. X cubed times x to the 4th is x to the 7th. X cubed times x to the 6th is x to the 9th. And so vertically, if I were to add, I get 1 plus x plus 2x squared plus 2x cubed plus 2x to the 4th, 2x to the 5th, and then I'm just going to say so on because we can see the pattern that's coming. So you see this process is tedious, and we actually have some things missing in here because I only multiplied a few terms by a few terms. If I went x to the 4th here, so let's add in that x to the 4th. x to the fourth times 1 would give me another x to the fourth. So this would actually be 3 of those, and then we would have an x to the 6th here, and then we have an x to the 8th, and so on. So we actually have, this is only correct up through the first 3 terms because I didn't multiply much out. We would actually have 3 of these, and we would have 3 of these. But you can see how this is a really tedious process to compute. If we needed to multiply more out, I'll show you how to do this in Wolfram Alpha. So I'm going to go to Wolfram Alpha, and I'm just going to type in what I want to multiply out. So I'm going to do a few more. I've got 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth times 1 plus x squared plus x to the fourth plus x to the sixth plus x to the eighth. And when I hit enter, there's my input. And then here's my expanded form. So you can see that I'm getting the same thing as when I did it by hand. 1 plus 2x squared plus 2x cubed. And then I have a 3x to the fourth, and the 3x to the fifth, and the 3x to the sixth, and so on. And we could multiply as many terms as we wanted just by tweaking what we're typing in here, and Wolfram can do it pretty quickly. But the goal is to figure out what does this expansion look like, and so we constructed the power series, that's what it's going to look like, and to figure out the interval of convergence. So we know that this one is going to converge on -1 to 1 because we wrote it as a geometric formula here. So that's going to converge. N equals 0 to infinity of x to the n is going to converge when absolute value of r is less than 1. And then that other one is x to the 2n, so that's x squared to the n. Thinking about this as x squared to the n, so my r is x squared. Squared has to be less than 1, and that's going to be on the interval from -1 to 1 also. Anything between -1 and 1 would make that a true statement. So my interval of convergence for that product, which is tedious to compute by hand, would be the overlap, which happens to be from -1 to 1. So now let's look at derivatives and integrals of power series. Suppose that the power series, the sum from n equals 0 to infinity of c sub n times x minus a raised to the nth converges on the interval from a minus capital R to a plus R, and that's an open interval for some r greater than 0. And let f be defined, be the function defined by the series f of x equals the sum from n equals 0 to infinity of c sub n x minus a to the n. So I've got this infinite polynomial I'm thinking about here. Then f is differentiable on the interval from the open interval a minus capital R to a plus R, and we can find f prime by differentiating the series term by term. So we could think about expanding it, and I could find the derivative of that series, or I could think about just using my power rule. I would bring the exponent down, right? I would subtract 1 from the exponent, and then we would take the derivative of the inside, and the derivative of x minus a with respect to x is just going to be 1. Okay, but notice when I take a derivative, I'm taking the derivative term by term. I'm just writing it really concisely as a summation. That first term is a constant. And when I take the derivative of a constant, I get 0. So instead of starting at 0, that derivative is going to start at 1. If I wanted a second derivative, that derivative would start at 2. And I would take that derivative the same way. So f double prime of x would start at 2 and go to infinity. I would keep the n, I would bring the exponent down, and then I would subtract 1 from the exponent. So my derivative would be the sum from n equals 2 to infinity of n times n minus 1 times c sub n times x minus a raised to the n minus 2. And that's going to work for the absolute value of x minus a is less than r. If we want to integrate f of x, we can integrate that power series. So we're going to use power rule. We're going to add 1 to the exponent, divide by the new exponent, which is the same thing as um, um, integrating each term separately. Don't forget the plus c when we integrate. Even with power series, we're still going to have that plus c because remember, this is a family of functions. So let's look at an example. We have f of x equals 1 over 1 minus x. We've talked about where that comes from. So that's the sum from n equals 0 to infinity of x to the n. And if we expand that, we're going to get 1 plus x squared plus x cubed, and so on. That's going to converge as long the absolute value of x is less than 1. We want to find a power series for g of x, which is 1 over 1 minus x quantity squared on the interval from negative 1 to 1, and then figure out endpoints. When we do take derivatives or integrate, the interval of convergence, the inside stuff's going to be the same, but for the interval of convergence, you must check the endpoints to determine if any of them need to be included. Okay, differentiation does not change the inside. Integration does not change the inside, but it can change what's happening with the endpoints. So, going back to example 6, we are trying to figure out a power series representation for g of x equals 1 over 1 minus x quantity squared. So let's look at f of x a little closer. F of x is 1 over 1 minus x. I could write that as 1 minus x to the negative 1. And if I were to take the derivative, I could use the power rule and chain rule. Bring the exponent down, subtract 1 from the exponent, take the derivative of the inside. So I'm going to get 1 over 1 minus x quantity squared. And that happens to be what I'm looking for. So if f of x equals 1 over 1 minus x, which is the sum from n equals 0 to infinity of x to the n, then g of x is the derivative of that. So it's f prime of x. We just found that to be 1 over 1 minus x quantity squared. So let's take the derivative of that series. So I'm going to start at 1 because I have to increase by 1. That first term is going to be a constant, and the derivative of that constant is going to be 0. I'm going to bring the exponent down, and I'm going to subtract 1 from the exponent. So I'm going to get n times x to the n minus 1. Now, it's fine to leave that way. This book does like to start at 0. So if I move this back to start at 0, then that means I have to change these n's to move up 1. So that's going to be n plus 1 times x to the n plus 1 minus 1, which is really just x to the n. Okay, either representation would be fine, but this book does like to start these power series at 0. So now let's figure out the interval of convergence. So we knew that the original series converged between negative 1 and 1. So original series for f of x converged between negative 1 and 1. So we really just need to check the endpoints. So let's plug in negative 1. And that negative 1 is going into my derivative because that's what I'm interested in. So I'm looking at the sum from n equals 0 to infinity of n plus 1 times negative 1 to the n. If we think about what happens, as n goes to infinity, this thing is going to diverge. And I can see that by just looking at a few terms. When I plug in 0, I'm going to get 1 times negative 1 to the 0. When I plug in 1, I'm going to have 2 times negative 1 to the first. And then when I plug in, so this is n equals 0, this is n equals 1. When I plug in n equals 2, I'm going to have 3 times negative 1 to the second. So I'm alternating back and forth between adding and subtracting numbers. So it's going to be 1 minus 2 plus 3 minus 4 plus 5 minus 6. And that's going to diverge. Now let's check the other endpoint. N equals 1. X equals 1 rather. So when I plug 1 in to that derivative, so I've got n plus 1 times 1 to the n, that thing is going to diverge also. So I'm going to have 1 plus 2 plus 3 plus 4, and that sum's just going to get larger and larger and larger. So that interval of convergence for the derivative would just be from negative 1 to 1. We would not need to include any endpoint. So let's look at part B. We want to evaluate the sum from n equals 0 to infinity of n plus 1 all over 4 to the n. So let's talk about what we know. We know the sum from n equals 0 to infinity of n plus 1 x to the n is equal to 1 over 1 minus x quantity squared. And that worked on the interval from negative 1 to 1. Or we could think about that as the absolute value of x is less than 1. So I want to know what's happening to n equals 0 to infinity of n plus 1 over 4 to the n. I'm going to think about this as a geometric series. So I'm going to think about this as n plus 1 times 1 over 4 to the n. So if I compare this guy to this guy, I'm replacing that x with a 1/4. So we're going to replace that x with a 1/4. So we're going to have 1 over 1 minus my x, okay, which I'm replacing here and here with the 1/4 squared. 1 minus 1/4 is 3/4. And remember, I'm squaring that. So I've got 1 over 9 over 16, which is 16 over 9. So let's look at this last example. We want to use some derivatives or integration to help us find a power series representation for each of these functions. Part A is looking at the ln of 1 plus x. So my f of x is equal to 1 plus x. If I take the derivative, f of x equals ln of 1 plus x. And if I take the derivative of that, I get du over u, which is 1 over 1 plus x, and I can think about it as 1 over 1 minus negative x. So I'm identifying my a and my r. I'm going to write that geometric series again up here. N equals 0 to infinity. AR to the n is equal to a over 1 minus r. So we found the a over 1 minus r. So then we can think about that sum. My a is 1. And my r is negative x. And I can write that as a sum from n equals 0 to infinity of negative x raised to the n. So if I were to expand this, I would get 1 minus x plus x squared minus x cubed and so on. Our goal is to figure out a power series for ln of x. So that rational function was easy to figure out power series for. So if I integrate this, I'll get ln of x. So if I integrate f prime of x dx, then what that means is I want to integrate that sum of 1 minus x plus x squared minus x cubed, and so on. And I'm integrating that with respect to x. So when I integrate the derivative, I'm going to get f of x, and this is going to be x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And if we see if we can write that as a sum, I could think about that x as x over 1 raised to the first power. So we see we have alternating signs. Let's start this one at 1 and go to infinity. So that first term is going to be positive. So I'm going to say negative 1 to the n plus 1. That will give me an exponent 2. And then my second term is going to be negative. If I plug in a 2, I'm going to have negative 1 cubed, which would give me that negative. So there's my signs. And this is going to be x to the n over n. So there's the power series representation for that one. So if we want to talk about interval convergence, we're going to go back to the original, which was our derivative that we found. And we know this guy is going to converge if the absolute value of negative r is less than 1. So that's going to happen on negative 1 to 1. This is going to be on negative 1 to 1 also, but we have to check the endpoints. It's always going to be on the inside. The inside's always going to be given, but we got to check the endpoints. So let's plug in x equals negative 1, and then we'll plug in x equals positive 1. When I plug in negative 1, and that's going in here, I'm going to have the sum from n equals 1 to infinity. This is negative 1 to the n plus 1 times negative 1 to the n over n. So this is the sum from n equals 1 to infinity. When I multiply and I have the same base, I would add the exponents together, so 2n plus 1 over n. So this is the negative harmonic series, which is going to diverge. And then when I plug in positive 1, I'm going to have negative 1 to the n plus 1. And this is going to be negative 1 to the n over n. Oh, just kidding. That's positive. Positive 1. n. I'm going to have the sum from n equals 1 to infinity. This is going to be negative 1 to the n plus 1 over n. We could use the alternating series test on this, and this is the alternating harmonic series, and we already know that thing is going to converge. So my interval convergence is going to be everything between negative 1 and 1. That's given when I take a derivative or integrate. And then you have to check the endpoints. Negative 1 did not converge, but 1 did converge. So this interval of convergence, this thing works as long as x lives between negative 1 and 1, including the 1. And then let's look at part B. Part B, we've got f of x equals the inverse tangent function of x. So f of x equals inverse tangent. I know if I take the derivative of that, it's going to be 1 over 1 plus x squared. I'm going to write that as a geometric series, so I'm going to think about that denominator as 1 minus negative x squared. So there's my a and my r. A is 1, r is negative x squared. So I'm thinking about this as the sum from n equals 0 to infinity of a times r to the n. So a is 1. I'm not going to write that. Negative x squared to the n. And if I were to expand this, I'm going to get a 1 when I plug in 0. And I'm going to have a minus x squared plus x to the fourth minus x to the sixth, and so on. So that's equal to the derivative. We want to know f of x. So to get f of x, we're going to have to integrate. So we're going to integrate 1 minus x squared plus x to the fourth minus x to the sixth, and so on. With respect to x, when I integrate the derivative, I get the original function. This is going to be equal to that inverse tangent. So we're going to have x minus x cubed over 3 plus x to the fifth over 5 minus x to the sixth over, oh, just kidding, x to the seventh over 7, and so on. Let's think about how we can write this as a series. So I'm going to start again at 0. This book likes to start at 0, if possible. So we do see signs are changing. So that first one's positive, the second one's negative. So let's use -1 to the n. The exponent, I started with an exponent of 1. So, and then I went to 3, and then I went to 5, and then 7. So they are odd exponents. Let's try 2n plus 1. That's a common way to write an odd number. And that's going to be over that exponent 2n plus 1. Now, I always like to check it. If I plug in 1, I'm going to get, if I plug in 0, I'm going to get x to the first over 1. If I plug in 2, I'm losing where I'm at. Sorry. If I plug in 0, I'm going to get -1 to the 0, which is positive 1. So my sign's correct. And this is going to be x to the 1 over 1. And then if I plug in n equals 1, I'm going to have -1 to the first, which is going to give me that negative. And this is going to be x to the third over 3. And if I plug in n equals 2, I'm going to have -1 squared, which will give me a positive for the third term. And this is going to be x to the 4 plus 1, which is 5 over 5. So you can see how this is producing the same sequence that I have here. And then so on. So this is correct. Now let's talk about integral of convergence. So again, we're going to go back to where we started. This geometric series, we know, converges when absolute value of r is less than 1. So the absolute value of -x squared has to be less than 1, which is going to be on -1 to 1. But we need to check endpoints for the integral. So I'm going to plug in -1, and then I'll plug in 1. When I plug in -1, I'm looking at the sum from n equals 0 to infinity of -1 to the n. This is going to be -1 to the 2n plus 1 over 2n plus 1. I'm going to simplify this. When I multiply and I have the same base, I would add the exponents together. So this is going to be 3n plus 1 as the exponent on the -1 divided by 2n plus 1. So when I plug in 0, I'm going to get -1 over 1. When I plug in 1, I'm going to get -1 to the fourth over 3. When I plug in n equals 2, I'm going to have -1 to the seventh. So the signs are bouncing back and forth over 5. And we'll do one more. So I'm going to have -1 to the 10th over 7. So I'm going negative, positive, negative, positive. So this guy, we could use the alternating series test on it, and we would see that this is going to converge at x equals -1. And then if we plug in 1, sum n equals 0 to infinity. Remember, I'm plugging 1 in for x. So I've got -1 to the n times 1 to the 2n plus 1 over 2n plus 1. Again, this is an alternating series. So this is -1 to the n over 2n plus 1. And this is going to converge by alternating series test as well. So for this guy, my interval of convergence is -1 to 1, including both of those endpoints. The last thing in this section talks about the uniqueness of power series. And this is just a theorem. Theorem 6.5 is just stating that power series have to be unique. So there's only one way to represent functions in terms of power series.